Finish this topic after a lot after a long break. I again uh, ki- trying to complete this course. Actually there was a pressure, so okay, so today will be the ninth lecture or 10th lecture. I am not actually sure. Let me see whether it is ninth or 10th. Just give me a moment. So this is okay, this is the 10th lecture, sorry. Okay, this will be the 10th lecture. Okay, what actually happened here? Okay, so now today we'll discuss as much as possible and try to finish it within two, maximum 2 to 3 lectures. Okay, the entire course. So now today we'll define something called Chinese remainder theorem, and let me recall whatever we have did last. So what we have discussed about the ideals and the homomorphisms, and what are the isomorphism theorems, the first isomorphism, second isomorphism, and the third isomorphism theorem. And last time we have already seen that the correspondence theorem. And now suppose I have two ideal, so you know the definition of I dot j or ij, the product ij, right? So if you have two ideal I and j be two ideal in a ring A, then what is the definition of ij or I dot j? This is all the possible finite sum of the type A dot B, where A inside I, B inside j, right? This is finite, right? This is all possible finite linear finite sum of the elements of the type A dot B. So can you feel that ij, this ij is an ideal of A. This is easy, just routine checking. Okay, you have to check it. This is verify, you have to verify this. So if you have two ideal I and j said to be co-maximal or co-prime if the ideal I plus j is equals to the entire ring A, right? Entire ring A. The ring A. Then we say that this I and j is said to be co-maximal, right? Okay, or co-prime. So for an instance, I can give you an example. I can give you an example here over here. So what is, suppose your ring A is zx, the polynomial ring over z, the coefficient transform z, right? So you have an ideal I is generated by x and j is generated by x minus 1. So you can feel that this x plus x minus 1 or 1 minus x minus 1 or 1 minus x is an element of x, right? Ideal generated by x, and 1 minus x is an element of ideal generated by x minus 1, right? So this is, what is this? This is 1, and this is unit in the ring zx. Unit, you can unit, the set of unit is defined denoted by this. So if an unit belongs to the an ideal, then the ideal will be the entire ring R, right? So this implies that this ideal generated by x plus 1 minus x or x minus 1, these are same. This is equals to the whole ring your zx. This is a simple example, right? Okay, so now let us come back to our main theorem. I will define what is called a Chinese remainder theorem. Suppose you have two ideals A and B be two ideals of a ring R, right? So let A and B be two ideal. Okay, so let me clear one thing. I will be little bit first from now onwards. Okay, it will be because I have to finish it as early as possible, so I will be go very first. Okay, this is two ideal of R, of ring R. So for R is a ring with unity or a commutative ring with unity. Okay, so just a second. Suppose A and B, if you have two ideal A and B of an ideal of R, and R is a ring with unity, right? So you want to define a map. Suppose F is a map. You want to define a map. Okay, just a second. Yeah, if you want to define a map from this ring to this R quotiented by A cross R quotiented by B, these are quotient ring, right? We have already defined what is quotient ring. So you can see this f of any element R is goes to R plus A, R plus B, and you can see this f is a ring homomorphism, right? It is very easy, obvious to check that if f is a ring homomorphism. What is the kernel of f? Can you see what is the kernel of f? Kernel of f is all those, this R is in R, so that this R plus A comma R plus B should be, what is the zero element in the ring of R mod A cross R mod B? This is A comma B, right? What is this? This is, that means that R plus A, let me R plus A should be equals to A, and R plus B should be equals to B, and this implies that R is in A, this implies that R is in B. R should be in A and R as well as R should be in B. That means that this should be A intersection B, right? So you know one thing very well, that A dot B as an ideal, the product of ideal is always contained in A intersection B, right? How? Why? Can you verify this much? So suppose you are an element, you have taken A from A dot B, what A will be look like? Then A will be look like some A1 B1 from finite sample dot plus AR BR, suppose. Okay, some AR BR. So each A1 B1 is a member of this B also, because this, you see here, this A1, because these AIs are from A and these BIs are from B, because now you can take this AI, see, you can take this AI to be from R and BI to be from B, then this element, entire element will be member of B. Again you can take this element to be from A and this element to be from R, so this will be member of as well as A. So this implies that the entire sum, this element, this element both are in A intersection B. So this implies that this A is an element of A intersection B, because this is also a ring, this is also a ring, so the it should be close under the operation, right? So this implies that your A intersection B should always be contained in A intersection B. So what about the converse? Is it always true that the A intersection B will be always, is it true that A intersection B will be contained in A dot B? Is it true? What do we think? Is it true? So yes, it is true, but provided your A and B should be your co-maximal or co-prime ideal, provided, otherwise you cannot say anything. But how we can show that? So this will do right now. So whatever you have, the map you have defined, see the map you have defined, this map need not be onto, right? Need not be onto, but I want to make this map to be onto. What is the choice? How I can make this map to be an onto ring homomorphism? so that I can apply the first isomorphism theorem, right? To show what is called a Chinese remainder theorem. Just forget about the name. Okay, so suppose A and B, you have this A and B are co-maximal. Suppose A and B are co-maximal ideal. So what do we think about? So co-maximal means that A plus B should be is equal to R. Is not it? A plus B, this is the definition of a co-maximal ideal. So if you have an element x from A and y from B, this means that for x is in A, y is in B, I can define this x plus y to be equal to 1, because R is a ring with unity, or R is a commutative ring with unity. So you can assume that here the R should be a commutative ring with unity, right? So now can you see that is it true? Can you see? Can you see this above statement is true? Suppose you have taken an element A. Okay, suppose you have taken an element from A intersection Y. So you already have this much of information, and you have taken an element A from A intersection B. I want to show this A inside this A dot B. So how can I show that? So you have this piece of information that x plus y equal to 1. So this implies I can multiply by ax plus ay equal to A. This implies that, see, I can, this, since the ring is commutative ring, so I can choose xa plus ay equal to A. Is not it? So this x is an element of A, and this A is an element of A as well as B. But for my need, for my what is called, I need this A to be in B. I want something what I need, A is in A, but that's okay. I don't need A to be in A, and this will help me something. So if I consider this A to be in A, that will not help us. But what this A, if I consider this A is in B, because A is in A intersection B, that means A is in A as well as A is in B, that I can consider this is in B. And here also this A is already in A, and Y is already in, A and Y is already in B. Is not it? This means that this A element is already inside this A dot B. This is the finite sum of an element of A and B, right? So this means that this A intersection B is a subset of, or is contained in A dot B. So we have shown that if your ideal is co-maximal or co-prime, then your A plus B, the A intersection B is exactly equals to A dot B. So now this is the way that I have defined something, and we have shown that this A intersection B is nothing but A dot B. Okay, provided the ideals are co-maximal, that means the sum of the ideal is actually. So I want to show that this map, the above map, whatever I have written, this map is an onto linear map, onto ring homomorphism. This F, I want to show this F is an onto ring homomorphism. So how I can show this is a onto ring homomorphism? So if I can show that this map is onto, then I have some interesting thing will be in my hand, right? So what I can do? So before that, so you have the map. Let me write it again. F from where to where? If F is a map from R, what the map is? Yeah, F is from R to R cross A, R quotiented by A cross R quotiented by B. This is my map, and A and B was my co-maximal ideal. That means that A plus B is equal to R. Okay, a plus b equal to r. This is my co-maximal ideal, right? So your map is from a, so what is my, any r goes to r plus a comma r plus b, and this map is a well defined map, right? So see, I have a piece of information that x plus y equal to 1. So from here I can write this x to be 1 minus y. This is in 1 plus y is in b na, 1 plus b. And also I have a piece of information that x plus y equal to 1. From here I can x minus 1 equal to minus y, which is in b. So this is b, which is in b. If and only if this x plus b is equal to 1 plus b, is not it? So what my f of r or f of x, f of any element, suppose x, this is x plus a comma x plus b, right? So for x plus a, what we can write, because x plus b is in here, so what I can write here, see, x is an element of a, right? So this means that x is an element of a na, so x is an element of a, so I can write it this to be a, because this will already dominated by this a, because x is an element of a, this x plus a is nothing but a. And what is x plus b? X plus b I have from here 1 plus b. Okay, what is f of y? Y is an element of b, and f of y is, f of y is actually what is y plus a, let me write y plus a, y plus b, but y is already a member of b, so I can write this to be b. But what is y plus a? Can you write something y plus a? Can you write something y plus a? So y plus a, you have to play with something in a similar manner to be here. So y plus a should be, okay, let me check first. Y plus a will be a member of, similarly you can do the same here from, so y plus b will be something a plus 1 plus a. Okay, how? The similar thing we did here, x plus y equal to 1, this means that you can take to be y minus 1, this is equals to x minus x, which is in a, so this is in a, if and only if this y plus b, sorry, y plus a is equals to 1 plus a. The similar kind of information I have chosen here. So similarly what I have, so fx is this, fy is this, where x is a member of y and y is a member of b, right? So now what I can do is here, so my claim is f is onto, now I claim that f is onto, and ring homomorphism, this is already, if you have, suppose you have taken an arbitrary element r1 plus a, r2 plus b, suppose I have taken, let r1 plus a comma r2 plus a, sorry, r2 plus b is a member of this r cross a, r mod a cross r mod b in the quotient ring, right? So I want a pre-image of this, that means I want some f of something, this should give you the pre-image this. Okay, then how I can show? So I claim that this f of r2x plus r1y, r1 will be my desired pre-image. So f of, that means f of r2, f of x by homomorphism property, f of r1, f of y, this is not it, this is r2 plus a comma r2 plus b with plus r1 plus a, because we have already defined r1 plus a comma r1 plus b. Okay, and multiply with 1 plus a, the image of p, image of y, 1 plus a comma b. This is actually nothing but you will okay, so there is a mistake here, so I have not multiplied here. So this is the image of f of r2, here r2, right? This is r2, and f of x. What is f of x? F of x is a comma 1 plus b and plus something. This is okay. So now what will be that be? That will be something like a comma r2 plus b plus r1 plus a comma b. This is the simple calculation. So this is a comma r2 plus b. Okay, that means that if you have such a thing, that you will be something like r1 plus a, you will multiply it by here and here. So you will get something like r1 plus a comma r2 plus b. This is your desired preimage. The preimage was this, right? The preimage of this is actually this. This is your preimage of this element, right? My handwriting is too bad. I apologize for that. Okay, so this map is going, this f is onto ring homomorphism. That means that R quotient by what by kernel a intersection b, right? This is isomorphic to, exactly isomorphic to R mod AB, because what you have, because AB is nothing but a intersection b, right? So this is isomorphic to R mod A cross R mod B. This is your Chinese remainder theorem. This is actually known as Chinese remainder theorem. This is known as Chinese remainder. In short, it is called CRT, Chinese remainder theorem, right? So I will define, I did for two ideal A and B, and I will define this for finitely many ideal, because you can definitely do by induction, you can do. So I will now formally define what is called the Chinese remainder theorem. Chinese remainder theorem is called CRT. Let me choose some another color over here. Yeah, so let R be an R be a CRU mat commutative ring with unity, and I1 dot IK be pairwise co-maximal ideals of R. Then the map, then this R, I don't know, I don't want to the map I1 intersection I2 intersection dot finally many IK. Okay, this is isomorphic to R mod I1 dot IK is isomorphic to R mod I1 cross dot cross R mod IK. This is called CRT. This is the actual Chinese remainder theorem, what is called the Chinese remainder theorem. But we will use some application, we will see some application of Chinese remainder theorem. Without application I will not do anything, okay? Because I have defined something, that means there is a purpose, right? Without purpose, why I am defining that? I am defining some theorem or some proposition. If I don't tell you why this is needed and why this actually where we can apply this theorem, otherwise you will not be able to learn anything. Because without just knowing theorem, what you will do? If you cannot apply anywhere, then what is the meaning of knowing theorem, right? So So what are the applications of Chinese remainder theorem that I will define right now? Okay, the applications. What are the applications of Chinese remainder? Suppose you know that that group Zn, right, or Z mod Nz. So suppose your ring is Z, and you have two M and N. Suppose that your GCD of M and N, this is 1. Okay, so you know that Z by Mz is isomorphic to Zm, and Z by Nz is isomorphic to Zn, right? You know that. What you know, the ideal generated by, or you can see that this Mz intersection Nz, you know that this is generated by GCD of M comma N, and GCD of M comma N is N 1, and this is Z, right? And you can see that this Mn, Mz plus Nz, that means this is co-maximal ideal. So what you can do, actually this is called ideal generated by M, and this is called ideal generated by N. Okay, so actually I should have to write this ideal generated by M intersection ideal generated by N is actually in Z. Okay, it's actually Z, and ideal generated by M plus ideal generated by N is actually Z. Okay, equivalent condition, these are actually same thing. So you know that Z mod ideal generated by M into ideal generated by N is actually isomorphic to Z intersection with ideal generated by M intersection with ideal generated by N, right, which is actually isomorphic to Z mod Mz cross Z mod Nz, right? So from here you can show, this implies that Z mod Mnz, what I am writing, Mnz is isomorphic to Z mod Mz cross Z mod Nz. Okay, this implies that this Z of Mn, this means that Z of Mn is isomorphic to Zm cross Zn, if this provided your GCD of M comma N is 1. That is what it is coming from the Chinese remainder theorem. Why this Zm is isomorphic to Zm cross Zn, provided your so that's one part, right? So just one piece of information, that one application I can say. What more application I can say? So do you have any other information? So as of now this information is enough, so I should not say anything more about that. Okay, so now I want to start a new topic, what is called an Euclidean algorithm, Euclidean domain. Okay, since as of now there was a basic ring theory. Okay, there was no complicated things. Now the thing is little bit, not too much, little bit, and conceptual is going to be happen here, and this is called in Euclidean algorithms, Euclidean domains, and principal ideal domain, and the domains that we have just now. As of now we have just considered with principal ideal domains and some PIDs and some of integral domains, right? So we have not discussed so far about something else, but today I will define something called Euclidean domain. And so how much the lecture? Okay, so Euclidean domain, let me start a new topic. It's called Euclidean, Euclidean. If I write slowly, then handwriting little bit somehow it readable, but otherwise if I write very quickly or very fast, then it is not it, it is not able to, I guess, readable. So what is an Euclidean domain? You know, in the Zn, in the integer for integer z, you know that the Euclidean algorithm, that what is called Euclidean algorithm or division algorithm, what is called the division algorithm. Okay, so before that Euclidean algorithm, I have to define something called a norm. What is a norm? Norm of a function, sorry, norm of a function. So what is called a norm? Norm is, suppose so as of now, whatever I have defined, this ring R is definitely, I'm assuming this R, by default I am assuming this R should be R, the ring should be an integral domain, must be, right? So let R be an integral domain. ID, I am short writing ID, integral domain. A function f from, sorry, not f, function is automatically comes in, a function n from R to, say, natural number union 0 with n of 0 equals to 0 is called a norm function. Is called norm function. A function, this is called integral domain, right? R be an integral domain, a function, this n, okay, the function n is called norm function. This is called a norm function. This is called norm function. Okay, so now I am going to define what is Euclidean domain. Euclidean domain domain. What is Euclidean domain? An integral domain. An integral domain R is called an Euclidean domain. In short, we can say this ED, right? ED, if there exists a norm, there exists n, which is called a norm on R with the property okay, this is called, this is written as property, with the property for every a comma b is in this R and b is non-zero, there exists a q comma r inside this the ring R, such that this a, any a can be written as some bq plus r, with r equals to 0 or n of r is less than n of b. This is the norm of R is less than norm of B. This is called an Euclidean. This is called an integral domain. An integral domain is called Euclidean domain. You know this result for set of integer, right? It is called division algorithm. It is called. But in any arbitrary ring, any arbitrary integral domain, if such a property satisfies, then we say that this ring is called an Euclidean algorithm, Euclidean domain, and we can write any element of this Euclidean, any element of this ring can be written as this pq plus r, with either r is exactly equals to 0 or norm of r should be less than norm of b. That's the idea. Okay, so this is called an Euclidean domain. So what more? So first the immediate thing that you should have to know about the what are the examples. You understood the definition. So what are the examples? Unless you do example, you will not understood the definition properly. Okay, the first example immediately should comes in your mind. Suppose this is your R is Z. You know, you have already know what is the norm function will be here. The norm of x you can take to be any x mod x. Then either your positive number here or negative number, this is mod x. So this satisfies your argument as a norm. Okay, this is an well defined map, right? example number 2. If you have any field, then you can define this norm to be this field to union 0. You can take what you can take. Okay, so if you have this field, then you have automatically you have satisfied this property. Suppose for every a comma b is in this field F and b is non-zero, a can be written as some bq plus r. You have to write in this format, right? R equals to 0 or norm of r is less than norm of b. So without loss of generality, you can take this r to be 0 because either this or this. So I can take r to be 0, this r to be 0. That means that a equals to bq. That means that this q equals to ab inverse. Q equals to a, q is here, or b inverse a. Sorry, this q is here, right? A equals to bq. So you want q. Yeah, you need b inverse a. So this is your q. The choice for q is this. See, the choice for q, I want to see. I know that you are facing some confusing something, that I have to define a norm, but how you are choosing this a equals to bq plus r first. So see, I have to define a norm with this condition, either r is 0 or norm of r. I need such a function, right? So that I can write any element of this ring as a equal to bq plus r. Something I can read. So without loss of generality, I can choose r to be 0. If I choose r to be 0, I can definitely write the element u, because you in a field you know that every non-zero element is a unit, right? So b is a non-zero element, b is a unit, so I can definitely multiply by b inverse, because in a field you know that every non-zero element is a unit, so you can definitely multiply by b inverse here. B inverse a, this is your q, just choice for q. You want a q, right? So this is called quotient. So I need a function that for which I can always choose this r to be 0, and what is called, if I can always choose this r to be 0 and I always multiply by b inverse, because b is a non-zero element is this field I have taken, so I can definitely multiply by b inverse. So that's why I have taken this a equals to bq, so that this q equal to the choice for q. I need the choice for q, right? What are the q and r? I need the choice for q and r, but I have already taken r to be already 0, but I need the choice for q. What is the value of q, so that this a can be written as some b into q. So this q, the choice for q is b inverse a. That's it. This is the basic idea. So if you have any field, then you can definitely, this is going to be an Euclidean domain. So any field, whether it is finite, infinite, I don't care, I don't bother. Any field is an Euclidean domain. Okay, if you have any field, so you can definitely say that this is an Euclidean domain. So now what else you can do? So if you have any field, that you can definitely immediate thing that should comes in your mind is the field, the polynomial ring over that field. Suppose your f is a field, and right, if a field, sorry, f is a field, and you want to, is it a Euclidean domain? Is it a Euclidean domain? So what are the norm? You will define the norm from fx to natural number union 0. Can you define this norm to be norm of x? Norm of any polynomial px is equals to degree of px. Will it work very nicely? See, if you have 0 polynomial, norm of 0, this is the degree 0 by convention. So this norm will serve your argument. This norm will serve your argument. This is your norm. Okay, but you cannot see this zx. If you have zx, is it is not an Euclidean domain. Why? Suppose you have an okay, why you can check, but ZX is not an Euclidean domain. I am giving you, suppose you want to divide by 2x plus 1 and an polynomial x is cube plus 4. What are the choices for your q and r? Suppose this is your a and this is your b. So you want to write this a to be some bq plus r. So what are the choices for r and q with the property that the norm is degree norm? So you will say that the choices for q and r will come that this will not be a member of this z. This will be definitely a member of q but not a member of z. Okay, some the rational polynomials will come, some p by q, the coefficient will be some p by q form. So this is not an Euclidean domain, right? So you know what is the Euclidean domain. Further go, we will define that every Euclidean domain is a principal ideal domain. So anyway, so let's keep it aside. Now what is called principal ideal? You know what is a principal ideal? You know, already know principal ideal. What is a principal ideal? This ideal, an ideal I is called principal if this I is generated by some single element A. Some A is in A, which is a ring. So this is a simple definition. Every element should be generated by a single element. So now there are some examples which is not an principal. So I will ask some question right now. Okay, so what are the principal ideals? So you can talk about, suppose if you have example, let's come to the example. Suppose you have z of square root of minus 5. You know this ring, right? What is this element? Actually a plus b square root of minus 5. Sorry, where a comma b is in z. So in the it is a ring, right? This is actually z plus square root of minus 5 z. This also can be written as in this format. So my point is, so is this, I am taking an ideal here. Suppose this 3 comma 2 plus root 5. Is it a principal ideal? Somebody could tell that this ideal is generated by two element 3 and 2 plus root 5. So this is 2 plus square root of minus 5. So somebody can say that this ideal is generated by two elements, so it cannot be principal. But who told you that this two elements can be generated by some one element? Who told you it cannot be generated by? So this, if you are arguing that this ideal is generated by two elements, so this cannot be principal, so it is your wrong argument. So you have to be very careful. There might be some element which can generate both of two elements, so that you have to verify. Is this an ideal? Is this an principal ideal? That's my question. So let's see. Suppose this ideal is a principal ideal. Suppose this ideal is a principal ideal, right? Okay, so I have to define some norm. I have already defined. So norm of what? This. Okay, yeah. So in this ring, I have to define some norm. Is norm of a plus b. A plus square root of minus 5 into b is actually a plus square root of minus 5 b conjugate. That means that a square plus 5b square. This is the norm. This is the norm over this ring. Over this ring, the norm is this. Okay, this is the norm. Actually, this is called field norm. But as of now, What if suppose this ideal is generated by some single element? Suppose this ideal I is generated by some single element. Okay, some single element of the ring. So your 3 will be generated by some alpha time a plus b square root of minus 5, and your 2 plus square root of minus 5 will be generated by some beta name a plus square root of minus b square root of minus 5. Suppose, okay, a plus b square root of minus 5. Suppose this element is generated by this two element. Now you know this norm, right? So let me formally define the norm on this ring. The norm of, let me use another color. Okay, so norm of in this ring, norm of a plus a plus square root of minus 5 into b. This is actually a plus square root of minus 5 into b into a plus square root of minus 5 into b. This is actually a square plus 5b square. This is your norm. So let's keep it aside and let's just use this. So 3 is actually your alpha times a plus b square root of minus 5, right? So norm of 3, what is norm of 3 will be? Norm of 3 will be 3 into 3 conjugate, that means 9. That means 9. So, and norm is a multiplicative function. Norm of alpha equal to norm of alpha, norm of a plus b square root of minus 5. See, norm of alpha beta, norm is a norm of alpha, norm of beta. Norm is a multiplicative function, right? You have to check this by the definition of norm. So what we get finally is 9 is actually norm of alpha into norm of, this is actually we have just defined here, a square plus 5b square. So this element is already in Z, because, or you can see this is in N, but more generally it is in Z. Okay, and this element is also in Z. So this 9, so this is, let's keep it aside. Now come to another. What is 2 plus square root of minus 5? They actually beta times a plus b square root of minus 5, because here now I am taking this. Now you can take the norm both sides. You can take norm of this norm of beta into the norm of this. What is the norm of this? 2 plus square root of minus 5 into 2 minus square root of minus 5. This is 2 square plus 2 square plus root 5 the square, that means 4 plus 5 is 9. This is actually norm of beta, and this will be a square plus 5b square. Is not it? So this implies that, see, norm of alpha. Okay, so you can divide 1 by 2. Suppose this is 1, suppose this is 2, so you can divide 1 by 2. That means the norm of alpha by norm of beta is equal to 1. Okay, so what more you can so what is norm of alpha? You have something like 9 equals to norm of alpha times a square plus 5b square, right? So what are the choices for a square plus 5b square? Okay, what is the choice for a square plus 5b square? What are the choice for a and b? Suppose your norm, see, your norm of alpha can be 1, suppose can be 9. If it is 9, then this is 1, can be 3, can be 1, because these both are integer. This is an integer, this is an integer, so you have to multiply by an integer so that you get 9. So this, if it is this 9, then this is 1, this is, if this is 3, then this is 3, if this is 1, this is 9. Okay, these are conjugate types of things. So suppose your norm of alpha is 9. This means that a square plus 5b square equal to 1. This means that a equals to plus minus 1. There is no other solution except plus minus 1. That this means that norm of a plus b square root of minus 5 equals to plus minus 1. Sorry, 1. So when this, okay, so norm of something is 1, this implies that this element is an unit. A plus b square root of minus 5 is a unit. So this implies that this is an unit. So if this is an unit, this then ideal, an ideal contains an unit, that means square root of minus 5, right? Similarly, you can choose the norm to be norm of alpha. If suppose norm of alpha is 3, what you will get, that a square plus 5b square equal to 3. A square plus 5b square equal to 3. But this does not have any solution in Z. No solution in integer. You cannot have any integer solution a and b in integer such that a square plus 5b square equal to 3, because you have at least, if you can, no, there is no solution. Okay, now the case 3 is norm of alpha equals to 1. So it will imply that a square plus 5b square equal to 9. That means that what are the solution for a and b? So b can be 0 and a can be plus minus 3. One kind of solution. B equal to plus minus 1, a equal to plus minus 2 is a solution. So this is some these are some solution. A square plus 5b square equals to 9, a equal to plus minus 3, b equal to 0. So b equal to plus minus 1, a equal to plus minus 2, and another solution. Okay, so now what we can do? Okay, alpha I have taken from this element. So these are some elements. Suppose this norm of alpha equal to 1. What does it mean from here, right? So norm of alpha, suppose an element, alpha is an element, sometimes c plus d square root of minus 5. This is equal to 1. What does it mean? That means the c square plus 5d square equal to 1, right? So c equal to plus minus 1, d equal to 0. So this means that this alpha equals to plus minus 1. But your 3 cannot be written as plus minus 1 times a plus square root of plus minus 5. Cannot be written. Is it true? See, I have to write, see whether I have to verify whether you can write this 3 as some alpha times a plus square root of a plus b square root of minus 5 or not. But you cannot write because you have a choice for alpha. Norm of alpha is 1. This means that this is this c square plus d square, but you have choice c is plus minus 1, d must have to be 0. This means that alpha has to be equal to 1 because alpha is key. C plus square root of minus 5 into d na, but d is 0. That means this is plus minus, c is plus minus 1. But this is an absurd. This cannot happen. So you have to choose. You cannot choose such a alpha. You cannot choose such alpha, right? Similarly, if we have 2 plus square root of minus 5 equal to some beta times a plus square root of minus 5 into b, but this is not possible because similarly contains the beta is plus minus 1 a plus square root of minus 5 into b, but this is also an absurd. So this ideal, whatever the ideal I have taken 2 comma 3 comma square root of 2 plus square root of minus 5 cannot be generated by a single element. So not principal, this I is not principal. This implies that this I is not principal ideal, right? Not a principal ideal. So okay, so this I is not a principal ideal. Okay, so principal ideal means, and what is called a principal ideal domain? Definition, okay, principal ideal domain. What is the definition of principal ideal domain? An integral domain is called a principal ideal domain, or in short PID, if every ideal is principal. That means AD ideal is single generated principal. This is a must a special case, that every ideal is generated by some single element. So now after that we will define something called a Noetherian domain, where an element and every ideal will be generated by some single set of generator. Okay, this is called a Noetherian domain. So as of now we will define some principal ideal domain. This is called every ideal is generated by some single one element, right? Okay, so just now we have seen that this z of example, a non-example actually, z of square root of minus 5 is not a PID, because this ideal, whatever the ideal, this ideal is not principal, and our definition says that every element should be generated by principal ideal. Every ideal is a principal ideal. So now last thing I am to do, but because I have to do something else right now. Okay, what is called, and another important thing is called every Euclidean domain. Euclidean domain is a principal ideal domain, PID. Every ED is a PID. How? Why this is true? Let R be a Euclidean domain, and this I is an ideal of R. Case 1, if I is 0 ideal, then we are done. If I is 0, there is nothing to prove because I is generated by 0. Case 2, I is non-zero ideal. So then you choose an element A which is an I but not a 0 element, right, with least norm. Because how you can choose? Because this norm, because every subset of a natural number have a least element, right? Least, it is called least norm of A, because norm of A is actually subset of natural number. Every subset of a natural number has a least element, which is called, what is called, is this called, I forgot, it's called well ordering principle. Sorry, this is called well ordering principle. So my claim is this I is generated by single element, which is A. Suppose B be another element in I. Let B be an element of then I. By division algorithm, because you are in a Euclidean domain, so you can write definitely there exists Q and R inside this ring, actually inside in this ring, what is called the ring R, such that this B can be written as AQ plus R, with R is 0 or norm of R is less than norm of B, norm of A. So this implies that this R equals to some B minus AQ. This is an element of I, because B is an element of I, A is an element of this ring, but Q is an element. Okay, what is the element? Okay, I is an element of, because A is an I na, so this B minus AQ should be a member of I with norm of, with similar thing, norm of this is this. So because since your norm of A is least, because you can take R to be 0, because this norm of A is actually least, so norm of R is less than norm of B is not possible. Since norm of A is least, so norm of norm of R is less than norm of A is not possible. So the only possible is R has to be equals to 0. This means that B equal to AQ. This means that B is a member of ideal generated by A. So this means that R is a PID. See what I am summarizing the proof. I have taken what I am claiming that R be a ring, R be a Euclidean domain, I is an ideal of R. Suppose I is a zero ideal, so I have nothing to prove, right? Suppose this I is a non-zero ideal. I have to show that every ideal of this ring is generated by some single element. Suppose I be an ideal of R, I will show that this I is generated by some single element. Non-zero ideals. Suppose A is an element is an I, but not is zero, non-zero element from I have taken with least norm. Okay, with least norm I have taken because there is a purpose. So I have taken this A with the least norm. Claim this ideal I is generated by something, this element A. I have taken an element in I, which I will see that I will show that this I is generated by this element. Suppose B is an element of I, which is, I will show that B is also generated by this A. Then I am done. If I can show that B is an arbitrary element of this ring, of this ideal I, if I can show that this B is actually generated by this A, then I am done. So I can apply division algorithm, because of this is an Euclidean domain. So there is this Q and R. Just a second. Okay, there is some element Q and R, so that B can be written as AQ plus R with norm of an R equals to 0 or norm of R is less than norm of A. Okay, so R equals to BQ minus AQ, which is inside this I, because R is an element of this I, but R has to be equals to 0 because norm of A is least. Norm of A is least, so you cannot have norm of R is less than norm of B. Since this is, so it cannot happen. So your only choice is R has to be equals to 0. So you have taken R to be 0, that means the B equals to AQ, that means B is generated by A. So this means that R is a PID. I have taken an ideal I, that this is generated by some single element. It cannot be. So this implies that this every Euclidean domain is a principal ideal domain. Okay, so I think I okay, now we'll define something is called something uh, the concept of GCTs, but let me okay, so I will define something definition here, just a second.